Let's see what is EMF and potential difference. We know that a source of electrical energy, say a cell or battery, when connected across the resistance, maintains a steady current through it. The cell continuously supplies energy which is dissipated in the resistance of the circuit. Suppose, when a steady current has been established in the circuit, a charge delta Q passes through any cross section of the circuit in time delta t. During the course of the motion, this charge enters the cell at its low potential end and leaves as its high potential end. The source must supply energy delta W to the positive charge to force it to go to a high point of high potential. The EMF E of the source is defined as the energy supplied to the unit charge by the cell. E is equals to delta W upon delta Q. It may be noted that electromotive force is not a force and we do not measure it in newtons. The unit of EMF is joule per coulomb or volt. The energy supplied by the cell to the charge carrier is derived from the conversion of chemical energy to electrical energy inside the cell. Like other components in a circuit of a cell also offers some resistance. The resistance is due to the electrolyte present between the two electrodes of the cell and is called the internal resistance R of the cell. Thus, a cell of EMF E having an internal resistance R is equivalent to a source of pure EMF with a resistance R in the series as shown in the figure 13.18. Let us consider the performance of a cell of EMF E and internal resistance R as shown in the figure 13.19. Voltmeter of an infinite resistance measures the potential difference across the external resistance R, potential difference V across the terminals of the cell. The current I flowing through the circuit is given by I is equals to E upon R plus R, or E is equals to IR plus I small r. Here IR is equals to V is the terminal potential difference of the cell in the presence of current I. When the switch S is open, no current passes through the resistance. In this case, the voltmeter reads the EMF as terminal voltage. Thus, the terminal voltage and presence of current switch on would be less than the EMF by IR. Let us interpret the equation 13.16 on the energy considerations. The left side of this equation is the EMF of the cell, which is equal to the energy gained by the unit charge as it passes through the cell from its negative to positive terminal. The right side of the equation gives an account of the utilization of this energy as the current passes through the circuit. It says that as the unit charge passes through the circuit, part of this energy equal to the IR is dissipated into the cell and the rest of the energy is dissipated into the external resistance R. It's given by potential drop IR. Thus, the EMF gives the energy supplied to unit charge by the cell, and the potential difference across the various elements account for the dissipation of this energy into various forms as unit charge passes through this element. The EMF is the cause and potential difference is its effect. The EMF is always present even when no current is drawn through the battery or the cell, but the potential difference across the conductor is zero when no current flows through it.